All right, chemistry, this is on the subject of solution stoichiometry. All right, so when performing solution stoichiometry problems, there are 4 standard equivalencies that can be used. So these are applicable to any. You don't use them all, but you use any one of these at any time. So it's 1 liter equals 1,000 milliliters. That's true for any liquid. 1 kilogram equals 1,000 grams. That's true for any substance. 1 milliliter equals 1 cubic centimeter. So milliliters are used for liquids, cubic centimeters are used for solids, but they're the same volume, exactly take up the same amount of space. And the fourth one is 1 milliliter of volume equals 1 gram for water only. That only applies to water. 1 milliliter equals 1 gram. Okay, so we're going to go ahead and do about 6 or 7 problems here. And the A problem on your assignment sheet will be done here on the video. The B problem you will do on your own. It is identical to the A problem, but the numbers are changed. So what is the molarity of 2.3 moles of potassium hydroxide in 250 milliliters of solution? Okay, so you got to remember what the definition of molarity is. It's moles of the solute, in this case KOH, over liters of solution. The solution is the KOH and the water together. Whenever you see molarity, you're going to convert it into moles over liters. Moles, in this case, of KOH over liters of solution. There's one exception, but we'll deal with that later. Okay, so what we're going to do is move forward here. So on the right-hand side, just like you always do, you set up what are you looking for. You're looking for molarity of KOH, or the solution rather. So it's moles of KOH over liters of solution. Okay, so over on the left, what we're starting with is moles of KOH and 250 milliliters of solution. Since we know we're looking for a final unit of moles over liters, we're going to place those two numbers, the 2.3 on top and the 250 on the bottom, like that. Okay, now the way you deal with these problems is, I call them two-story problems. You have a top story, the numerator, and a bottom story, the denominator. So first we're going to deal with the numerator. We're going to make any conversions that we need to make. So there we go, and we start with moles of KOH, and we end with moles of KOH. So there's no conversion necessary. You're already in the units that you want in your final answer. So now we go to the bottom story, the denominator, and we're going to have 250 milliliters, and we need to convert to liters. And we're going to use one of our 4 standard conversions of milliliters to liters. And so the one we use is 1,000 milliliters equals 1 liter of solution. So you just have to decide which one goes on top, which one goes on bottom. Think about it. There's the 2 conversion factors, and we are going to use the first one on top, okay, the second one on bottom. So it's 250 milliliters times 1,000 milliliters over 1 liter. Milliliters cancels, and now what you have is liters of solution on the bottom, and that's what you wanted. So now you're ready to compute the answer. Moles of KOH on the top, liters of solution on the bottom. So you multiply everything on the top, 2.3 times 1,000 divided by 250 divided by 1, and that gives you 9.2 molar is the way you would say that. Moles of KOH per liter solution, or 9.2 molar. Okay, now how many moles of HCl are there in 350 milliliters of 1.7 molar aqueous solution? So when you have molarity, you convert it to moles of solute over liters of solution. In this case, the solute is HCl. So what we're looking for is moles of HCl. So we're going to put that over on the right side. So the top part of the problem moves from moles of HCl to moles of HCl, so no conversion is needed. There you see it there, right there. So now what we have on the bottom is liters of solution, and we have nothing on the bottom in the answer. In other words, we need the liters of solution to disappear. Okay, so how are we going to do that? Well, it's going to take a couple of conversions. So we use the liters of solution to milliliters, and then with the 350 milliliters of solution, it looks like this. So you put 1 liter, that's one of our standard conversions, of solution over 1,000 milliliters. and then you multiply by 350 milliliters. Again, what you're doing is setting these up so the units of measure cancel properly. So liters of solution, milliliters, milliliters. So now you notice there's no units on the bottom anymore. They all cancel. And on the top, we still have moles of HCl, which is what we want. So now we're ready to run the numbers. 1.7 times 1 times 357 divided by 1,000, and that gives you 0.61 moles of HCl. Okay, so here's one. You want to create 500 milliliters of a 1.2 molar NaOH solution. How many grams of NaOH would be required? This is a question they could ask you on the advanced placement test. Your teacher tells you, I want you to create 500 milliliters, a certain volume of a certain concentration, 1.2 molar NaOH. So your job is to go back in the storeroom, get the NaOH, measure out how many grams you would need to create that solution. So the numerator, the top of the problem, moves from moles of NaOH to grams of NaOH. Okay, so that's a molar mass conversion. So there we go. So on the right, you want to try to find grams of NaOH. That's the question's asking you for. On the left, you're starting with the molarity. 1.2 moles of NaOH per liter of solution. That's molarity. So the first conversion is going to be moles to grams. And then on the bottom, we need to get liters of solution to disappear because there's no denominator in the final answer. So the denominator in the bottom of the problem moves from liters to no units, so liters of solution must cancel. Okay, so we're going to start with the molar mass. We're going to start with the top part of the problem. Do the problem one part at a time. Top part, then bottom part. So we're going to use the molar mass of NaOH. You compute that from the periodic table. There it is. Okay. And now what we're going to do is moles of NaOH cancels with moles of NaOH, and what you have is grams of NaOH on the top. That's what you want. That's what you want for your final answer. Now we got to get the liters of solution on the bottom to go away. Okay, now on the bottom we need liters of solution to cancel out, so we're going to use the 1 liter of solution equals 1,000 milliliters of solution to get into milliliters. And then you notice we have a number to work with up in the problem, given to us in the problem, 500 milliliters. So we're going to use those two conversions to cancel out the liters. So it looks like this. 1 liter solution for every 1,000 milliliters, that's a standard conversion. And then you multiply by 500 milliliters given to you in the problem. So liters cancels there and there, milliliters cancels there and there. You'll notice that there are no more units on the bottom. So now we're ready to go ahead and calculate our answer. And if you multiply 1.2 times 40 divided by 1,000 times 500 divided by 1,000, you get 24 grams of NaOH. Okay, what is the mass percent of 8 grams of strontium oxide in 45.2 grams of solution? Okay, so here's the equation. It's given on your formula sheet. Mass percent equals grams of solute over grams of solution times 100%. Now there's a trick to this problem you have to be careful of. Did they give you grams of solution or grams of water? They gave you grams of solution. So you simply need to do the following. You need to put 8 grams of SRO over 45.2 grams of solution times 100%, and that gives you 0.15 times 100%. So that's going to be 15%. That's the mass percent of SRO. If they had given you 45.2 grams of water, that would be the solvent. To get the solution, you'd have to add the grams of water and the grams of SRO together. In other words, the 8 and the 45.2 together. That's if they had given you 45.2 grams of water. You would have had to add them. Here you didn't have to add them because the solution is both the water and the SRO together. And so you did not need to do that step. If a 100 gram solution is 5.2% NaCl by mass, how many grams of NaCl does the solution contain? Now this is not a problem I normally want you to compute. I want you to just know the answer to this because we talked about this before. You simply assume that you have 100 grams of solution which in this case they tell you do. So 5.2% by mass is going to convert to 5.2 grams. That's why you choose 100 grams. We talked about that. So the mass percent equals grams of solute, NaCl, over grams of solution, that's the NaCl and the water together, times 100%. Okay, so we're going to work the problem backwards. We have 5.2% we're given, and we have 100 grams we're given. And so what we're going to do there is divide both sides by 100% and multiply by 100 grams, and that'll give us our answer in grams. Okay, and what that gives us is this. 5.2 grams of solute. Again, I don't want you to work that calculation. I want you to just know that if you're given a mass percent, you just convert it to the same number of grams. Just remember that principle, and you can't go wrong. Okay, what is the mole fraction of 25.2 grams of potassium chloride in 102.4 grams of H2O? This is very much like a mass percent problem, except you're not dealing with grams, you're dealing with moles. And you can see that you're given grams in the problem, so you're going to have to convert to moles. So you need to use the molar mass conversion. So there's mole fraction. It's moles of solute over moles of everything in the solution. It could be more than one solute, but in this case it's just one. Okay, so KCl and H2O are given in grams and must be converted to moles. So the solution is both of them together. So there we have 25.2 grams of KCl times 1 over the molar mass of KCl, 74.55. You do that, compute that from the periodic table, you get 0.34 moles of KCl. For the water, 102.4, you divide by the standard molar mass of water, 18.02, and you get 5.7 moles of water. So now, remember, you have to have solution in the denominator here, and you're not given solution. You're given 102.4 grams of water. So to get the solution, you have to add both of them together, the 102 and the 25.2. Be sure you understand that distinction. So there we do that. On the bottom, we put 0.34 moles plus 5.7 moles. And in the numerator, it's the KCl, 0.34 moles. And there you go. You get the mole fraction is just expressed as a decimal number, not really as a fraction. Okay, what is the parts per million of 0.2 grams of arsenic in 2 kilograms of solution? So you use parts per million. It's the same as mass percent, except instead of multiplying by 100, you multiply by 1,000,000. It's used when you have very, very small amounts of a solute in the solvent or in the solution. Okay, so parts per million problems are just like mass percent problems, except the ratio is multiplied by 1,000,000 instead of 100%. Parts per million measures are used when the amount of solute is very small. Okay, so there's the formula that's on your formula sheet. And notice that you are given 2 kilograms of solution, so you don't have to add the two together. But you got to convert from kilograms to grams. You cannot have one measure in grams and the other in kilograms. You have to be in the same unit of measure. Okay, so first, kilograms must be converted to grams using the equivalency, one of our standard conversions. 1 kilogram equals 1,000 grams. So there we do that conversion and we get 2,000 grams. That's what 2 kilograms equals. Now we're ready to plug into the formula above. Cancel, cancel. And now you have 0.2 grams of arsenic over 2,000 grams of solution times 1,000,000. And that would give you 100 parts per million is the concentration there. Okay, what is the molarity of 8 liters of 3 molar solution if it is diluted with 4 liters of water? So this is the lemonade problem. You made the lemonade too strong, so you wanted to thin it out and make it more dilute, so you pour more water in. And so that's what's going on here. That's what dilution is. Now this is the one problem where you don't have to convert molarity into moles of solute over liters of solution. Just leave it as a molarity, and it's a very simple formula. Okay, so this is a dilution problem. If you make a pitcher of lemonade and you add too much lemonade powder, you would dilute the solution to make it less sweet. Okay, so there it is. There's the formula. The molarity before the dilution times the volume, how much you have before the dilution, equals the molarity after the dilution, that is after you poured the water in, times the volume after you diluted the solution. Okay, so the problem says that you are adding 4 liters to 8 liters already in the beaker for a total of 12 liters. Okay, be sure you see that. So it's going to be molarity is 3 times 8. Molarity before it is 3 and volume before is 8. And molarity after is going to equal M2 times the 8 plus the 4. You already had 8 liters. Now you're adding 4 more, so that's 12. And if you do the math on that, you have 24 divided by 12 equals 2 molar. Okay, so you made the solution. It started off 3 molar. You made it weaker. You made it less concentrated, 2 molar. All right, and that takes care of this first lesson on solution stoichiometry. It's a bit more involved than molar mass, grams to mole stoichiometry, but it's the kind we're going to use quite a bit going forward.